Well, hello, thanks for watching. In this video, I'm going to analyze an elliptical orbit. And you may have seen my video on the circular orbit. I want to try to draw some comparisons between those two things to see what you can do with an elliptical orbit versus what you can't do that you could maybe do with a circular orbit. So the first thing I want to show you is what you can do quite easily for an elliptical orbit that you also did for a circular, and that is to find the period of the orbit, how long it takes to orbit one time. So what I've done here is I've just drawn an elliptical orbit. I'm going to imagine that this is Pluto. I actually went online and found a little information about Pluto, so I included here its mass, and I've got its near and far distances from the Sun. Notice here in an elliptical orbit, we do not have the Sun at the center of the orbit. We have it at what's called a focus of the orbit. That's off to one side. So there's a near point, I called it N. There's a far point here, I called it F. And then there's a random point down here, I just called P for lack of a better name. So our ultimate goal will be to describe what's going on at each of these 3 points. Now, one of them I just looked up. You're going to have to know something about the orbit at one point to be able to know things at other points. And that, of course, is the nature of a lot of physics problems. Tell me something about the situation in one state, and I'll try to figure out what's going on at the other state using the laws of physics. So in this case, calculating the period, we've got a very similar equation to what we used for the circular orbits, except that we do not have a radius here. We have instead what's maybe sometimes thought of as a radius. If you draw this incorrectly and it looks too much like a circle, you might actually be tempted to call this a radius. But it's actually the average distance from the Sun. So turns out if we know the near point and the far point, if we just take the average of those two, we call that the length of the semi-major axis. We give it the symbol A. So here I've got these two measurements, 4.4 and 7.4 times 10 to the 12th meters. So the average of those is 5.9. So what we do is put that in, 5.9 times 10 to the 12th meters. That has to be cubed. And then we're going to use our universal gravitation constant, which I'm not going to write out. It's kind of lengthy. And then the mass at the center of the orbit. Now, in this case, it's not at the center, but it's at a focus of the ellipse. And that, of course, is the Sun with a mass of 1.99 times 10 to the 30th kilograms. So you crank all this through, and you get a kind of an ugly number, 7.82 times 10 to the 9 seconds, which is not a very convenient unit to measure in. So we would certainly convert that into something better like days or years. It turns out in this case, you could divide by the number of seconds in a year, and you're going to get about 247 years. Now those are Earth years that we're talking about. So an awful long time for Pluto to orbit once compared to us. Of course, that's because it's so far out. One of the important things that Kepler learned and described it in his third law is the further away from the Sun a planet is, the longer that orbit takes. So it'd be interesting to see if you could do a Kepler's third law proportion. If you know how far Pluto is from the Sun on average and compare it with the Earth, you can do this same problem and get 247 without all of this other information. But that's for another problem. So the next thing I'd want to describe is the velocity. Now, for a circular orbit, you just say the velocity of the orbiting object. But in an elliptical orbit, you don't have a single velocity. You've got a velocity that's changing all the time. So here at its near position is where it's moving the fastest, and I happen to know that. I looked that up. So out here somewhere, you would have a smaller speed, and here you would have something in between. So we've got this constantly changing velocity vector. Now I picked these 2 points because notice, because the velocity is tangent to the orbit, that it makes a nice 90-degree angle with this major axis. But here at point P, it does not make a 90-degree angle, and so I'm going to show you that you'll have to find the speed a little differently here than you do here. I'll do the easy one first. The velocity at that far point F. We're going to use conservation of angular momentum. I'm going to use the abbreviation for angular momentum, L. This is something you first studied in your rotation chapter. And it says if you can pick an axis around which something is rotating, and I think a natural point here is the sun, that a force caused by that sun cannot torque the system. So it might be exerting a force causing its motion to change, but we are not exerting a torque. And if there are no torques exerted from the outside, then we have angular momentum that is conserved throughout the orbit. So if we can describe what the angular momentum quantity is, we will be able to find out how fast it's moving out here. So the angular momentum, I'll describe that here as R cross P, or RMV times the sine of the angle between them. So R is the vector that goes from the sun, the axis of rotation here, out to where the planet is. M, of course, is the mass of the moving planet. This is Pluto. V is the velocity of the planet at that point. And then theta is the angle between R and V. So the reason I'm using that for these two positions is because the angle is 90 degrees. And I don't have to worry about the sine of 90 degrees. It's just equal to 1. So when I write all this out, so I would say R at that near point times the mass of Pluto times the velocity of Pluto at the near point times, again, the sine of 90, which I'll leave out, is just equal to R at the far point times the mass of Pluto times the velocity at the far point. And you see how this very nicely just becomes a simple proportion. So I could find the velocity at the far point just by dividing by my distance out there. So I'm not going to show the rest of the work here, but I will tell you, you will get about 3,640 meters per second out here. Okay, so that's using conservation of angular momentum. Again, it works great for these 2 points here because we don't have the angle to deal with. But I'm not going to use that here. Now, I could somehow try to find that angle. I wouldn't know how to do that, to be honest with you, because I like to work these a little differently. There's another quantity that is conserved in an orbiting system, and that is, I'll show you here, to find the velocity at point P, we're going to use conservation of energy, which means the potential energy and the kinetic energy, although they're different at every point in the orbit, the total energy will be the same. So let's remember how we describe the energy. Potential energy, we cannot use the old mgh that you might be used to using for objects here on the surface of the Earth. We've got a different quantity for potential energy. We call that U sub g. It's equal to the negative of big G, the gravitational constant, times each of the 2 masses. So this is the mass of the sun times the mass of the planet Pluto, divided by whatever the separation is between their centers. And so that's why we need these distances here. So we're going to have to know this distance from center to center, which I just picked a spot, wrote down a number, and said, let's find the velocity there. So you see how, because we know these 2 R values here, we could find the potential energy at all of these positions, and I do know the velocity and therefore the kinetic energy at this position. So with this information here at point N, I can get the total mechanical energy of this system, and then I can set it equal to what the energy should be at point P. So I'm not going to show all of the details here because we're getting close to 10 minutes and I want to get close to wrapping it up, but let me at least write out what this would look like. It's going to be kind of long, but at point N, the potential energy is negative G times the mass of the sun times the mass of Pluto divided by that distance there at N. I labeled it minimum, but I should probably have just labeled that R sub N. And then I have 1/2 mv squared, where again, this is the velocity at that same point. Still talking about the moving object. We're imagining here that this sun, everything is being measured relative to it, so it's not moving. So the mass of Pluto times the velocity at that point squared. So again, all of these numbers we would know, just plug those in. And then we're going to set it equal to the same energy expression out here at point P. So negative g, mass of the sun, the mass of Pluto, divided by this distance here at P. Be careful you're not squaring this. I always caution students not to square. They're so used to squaring things in denominators when they do the law of universal gravitation that they want to keep squaring it even when they're doing the energy equation. So again, we would know all of the numbers here, and then we have 1/2 m times this velocity, and that right there is the velocity we're trying to determine. So I would put all the numbers in, and then I could solve for that. And I did this previously, and you can trust me. It'd be a good exercise for you to put this in your calculator yourself using the parameters that I gave you. Make sure you work it out, but you will get a velocity right around 4,250 meters per second. And does that seem reasonable? Well, of course, we know it's got to be between the highest velocity here at the near point and the lowest velocity here, which was around 3,600 and some. So that makes sense that it would be in between those things. So again, if you want to crank through that yourself, that would be great. But I've at least shown you how we can use either conservation of energy at any position, because notice we did not need the angle to do energy. Or at these two special spots, we can use conservation of angular momentum. Both are great tools that you can use to solve for elliptical orbits. Hope this was helpful for you. Thanks for watching.